is Rebecca Golden. She's a professor of mathematics at George Mason University. She has a PhD in math from the Massachusetts Institute of Technology. Lest any of you think that we bring lightweights into this group. It doesn't happen. She also is the director of research for the Statistical Assessment Service at George Mason University. And in that role, she interacts regularly with journalists. She does seminars for journalists, and she talks with individual journalists about specific stories. So journalists who are looking at a report and want some help analyzing the importance of it or the meaning of the statistics can call Rebecca, and she can walk them through how to look at that and talk about it. She also helps journalists sometimes at the beginning of the reporting. If they say, I'm looking at XYZ, what numbers do I need? Or how should I structure my questions or my search? And she can talk more about this, but my point is she's very experienced at talking to journalists. And that's why we brought her here today to talk a little bit about reading scientific papers. Rebecca, I'll tell you, an earlier speaker made reference to some statistical element of reports. What was it where she said, have you had that yet? And I said, no, Rebecca's going to get
the two types of risk.
Different types of risk. So you may want to
Great.
grab that at some point.
Great.
We have a handout, but I'll let you
a little
pass
bit.
it out when
Okay.
you're ready.
Great. Well, first, thank you so much for letting me come and talk to such a distinguished group of people. I have been incredibly humbled in this experience. When I joined Stats about 10 years ago, we all kind of live in our own worlds, and I hadn't really talked very much to journalists at all, and I knew a lot of mathematics, and that was why I was brought in. And I have learned so much about your trade by talking to people, and I feel, thank you, that you guys have quite a challenge, often without the support that you need to do. Can everyone hear me now? Okay. Often without the support that you need to do what it is that you're tasked with doing or what it is that you'd really like to report on. And what I've found over the years is there's a number of sort of cultural compromises that are made within journalism, and that goes true also for scientific research. But I want to kind of put a caveat on this, which is that I was trained as a mathematician, not a statistician. This has actually been a tremendous advantage for me because I've had to learn a lot about statistics over the time that I've been in my position here, specifically with the aim toward how do you understand in broad strokes some of the research that's being done, rather than the way a statistician is trained, which is how do you actually run an analysis? What are the correct tests to use for an analysis? Those are very different questions than what do the results of this test mean? So what I'm going to try to walk you through a little bit here are what are the sort of areas in which we see a lot of mistakes done by journalists and easy improvements to be made, sort of like low-hanging fruit, if you will, and also a few kind of comments on actually like what are the statistics telling us, what are the kinds of things that we can learn without having a year as a graduate student in statistics. And also I just kind of wanted to start by saying a couple words about our organization, because stats.org recently kind of died and got reincarnated, if you will, with the invention of Sense About Science USA. So Sense About Science UK is a well-established organization. We have created Sense About Science USA, and Stats is a branch of that. So I'm continuing in my same role, but if you were to look up our organization, you would currently see an outdated website which is about to be replaced with an entirely new one at stats.org. You're welcome to look at it. Be wary of viruses. It's not being well maintained. But within a couple weeks, a new one is going to go up. And that's because of this new merge with Sense About Science USA. So a lot of recent material I've written, for example, is not even posted yet because we're all waiting for the new launch of the new website. And that's a very exciting endeavor. And one of the things that we're doing with that is pairing up in a very tight relationship with the American Statistical Association with the idea of creating a pool of statisticians who are available right now to journalists, because the time frame is often what's really really important here. So I didn't realize here that it's not all. Okay, so that's what this was a past slide. I apologize. All right, so let me just start with saying what it is that we talk about in journal articles that are that come up all the time and that are really sort of basic concepts that really need a clear understanding. Things like the mean, median, and mode, you probably all are aware of this, but it's actually can be really important because the mean is something, it's the average, like the sum of the numbers divided by the number of people, but it's one of those things that's actually very highly influenced by outliers. That's why when we talk about income levels, for example, we usually don't talk about mean, but we talk about median, which is the halfway mark. If a median income is something, that means half the people make more, half the people less, and we don't worry about what gets influenced by the Bill Gates among us, right? But it also is important in reporting about cancer. An example of one I came up with recently was talking about median survival rates. They were talking average, they use the word average, and all of these things can be called averages. Average survival rates of a treatment for breast cancer. And this was a very foolish set of articles actually published in the New York Times. Nope. but in fact by a bunch of oncologists even who wrote it wasn't
Not
actually
by me,
this
'cause I have struggled
this is
with that.
something that actually the New York Times wasn't at fault. So it was actually a group of oncologists who wrote a letter to the New York Times that was published. I'm pretty sure it was New York Times about the inefficacy of certain medications because look at what the average lifespan of the women who were on these drugs were, and they showed it was only in sort of a few months of increased lifespan. But to put this clear, if you're talking about a median, it means half the people lived longer, half the people didn't. So you could imagine, just as a theoretical example, a cancer medication that cured 50% of the people, or say 49% of the people, and the others it didn't have any effect on and they died within 3 months. So then you would in fact have a median of 3 months because more than half the people died within 3 months, but a 49% cure rate for terminally ill women with breast cancer is a phenomenal accomplishment. So talking about the average in that context could be really misleading. You'd really want to understand not just what the average is, the median in that case, but also what are the spread of the data. And that's one of the things that comes up next, which is called standard deviation, which is a measurement of how much the data are spread out from that median. We talk about confidence intervals, and a lot of people get very confused about confidence intervals. We talk about 95% confidence interval, and it does not mean that 95% of the data lie in that interval. What it means is that if we were to rerun an experiment, 95% of the time we would expect to get in that range. It's a very important concept, and it'll come up again. In fact, one of the things that I did was I brought a sample study. I tried to make it about cancer because of the focus of this group. And if we have time, I'd like to pass around and kind of talk about how do we actually, in practice, read these things and understand the statistical concepts that come up. Orders of magnitude are strangely difficult for people. We often understand, 10, 100, 1,000, but then we get more confused when we talk about milligrams, micrograms, etc. That's sort of more a general thing, confounding factors, what gets in the way of the measurements that we're making, what kinds of things could come up that might make us, the statistics look one way, but in fact, we're measuring something incorrectly. And it's, again, a really important thing, especially in health research, because people have so many different things that they do with their lives. Percentages, of course. I think I won't talk so much about that. I'll talk a little bit about absolute versus relative risk. And this is really important because a lot of times the best that we can do in measuring in a study is a relative risk. And in fact, I don't know what the previous speaker spoke about when she said different kinds of risks and ratios of risks, but a lot of times the best we can do is actually speak about something called an odds ratio. And an odds ratio, you don't even know what those absolute risks are. You can kind of compare the risks of two groups without knowing what they really are. And it's a profoundly important thing when we're studying especially rare diseases, but it's not something that tells us what our actual risk is. And I will bring that up later on in this. But the concept of absolute risk is this is the risk you will undertake if you, whatever it is, fill in the blank. So the study that I brought is here to talk about, was in the news recently, was about nut consumption and death rates, including death due to cancer. And it talks about, well, this is your rate of death if you are a nut eater, and this is your rate of death if you're not a nut eater. And those are absolute risks, meaning that's what they can anticipate based on this data. And that's very different from how do you as a nut eater compare to me as a non-nut eater? What is your relative risk? And so if you say you're 50% less likely to die, what does that mean? And it's only in comparison to somebody else. It's not actually what your risk is. Okay, scientific methods, how do we design studies? I'm going to talk a little bit about that today, and that the impact of how that comes about. And then the big one, causation versus correlation. Extraordinarily important and typically really misunderstood, not because we don't understand it in the abstract. I mean, abstract is so obvious, right? Causation does not equal, correlation does not equal causation. And we know of so many examples of things that at least we believe are only correlated and not causal. But at the same time, we often, it's really easy to watch our biases creep into this. So if we kind of believe something, then we are really, really quick to jump to, well, it's probably causal. Whereas if it's sort of obviously a ridiculous association, we're really quick to say, not really. And some of that has to do with something that's valid, which is sort of trying to understand the mechanisms by which something might happen, which is really important research, but sometimes it's just our biases, and it's actually quite difficult to decipher. In cancer research, less so, I think, than in a lot of other work where it's has many more confounding factors involved, and I might mention some later in this talk. Okay, so here's the process, right? You guys are handed a press release. What do you do with the press release? Well, the first thing I hope you do is you understand that it's not going to tell you the whole story. It's actually designed to get your attention. There are professionals in most universities and in medical centers who write these press releases, and their goal is to get it reported. The more press they get, the better it looks for them. So they're going to present their results in the rosiest terms possible. The person who's writing the press release may not be the person who wrote the original paper. Sometimes it is, but sometimes it isn't. So you should view that as an advertisement. Do you believe everything that's told you in advertisement? No. Is there some truth in it? Sure. So it's worth then looking for what the abstract of an article will tell you. So you might say, well, I'll go look this up on PubMed. All of you are familiar with PubMed? You go there routinely? How many of you has never heard of PubMed? Anyone never heard of PubMed? Okay, so PubMed is like a central database for searching for articles. Press releases will often say it's published in and then give you a reference. And if it's been referenced, it will be available in PubMed to look at the abstract. The abstract itself has some limitations. I've rarely met journalists who go past the abstract, and I want to encourage you to consider that next step. There are reasons for it. I mean, you're often being asked to pay money to go past it, and $30 here, $30 there, and all of a sudden, so it's not unreasonable to be put off by that. There are ways, by the way, you could just email any faculty at any university. They can usually get hold of it for free. You can email the authors of the study. But it's actually important because there are a lot of questions that are not answered in the abstract that will tell you really fundamental things about how believable the study is. One of them includes how did they get their candidates for study, like who's included in the study. If you're, what's the design of the experiment? So again, to use breast cancer as a reference point, if you're going to write an article about whether mammography is helping or hurting women who are getting mammograms, you want to ask the question whether are they simply comparing women who had mammograms to people who didn't, because maybe people with a history of breast cancer in their family are more likely to pursue the medical treatment or what they view as preventative care, or more observational data, therefore more aggressive about treating it, therefore they're catching more cases. On the other hand, the data could go the other way. If women who have a greater history are also more likely to get mammograms, you might see increased risk of breast cancer associated with mammograms that has nothing to do with mammograms. You won't find that information unless you're reading how they collected the data. Did they consider that possibility without knowing whether they did it right, the consideration of that possibility, but did they consider it? And it will be in the article. Okay. And this thing about the weaknesses of the conclusions, I always tell people, if you have limited time, in addition to reading the abstract, go to the conclusions section. Usually authors will say, here are the limits of our study. And usually they'll say, this is a limiting factor, however, we dealt with it. So, they're saying it shouldn't really, cast any doubt on it, but I think it's still nonetheless, it usually it'll give you something to sniff at, if you will, kind of something that might be something to pursue a little further, look at, and ask other people whether there's controversy over those issues or the design of the study. But they will tell you quite explicitly what the weaknesses of the design of the study are in quite simple terms. So it's really a useful thing to kind of look at that. Okay, so here are the easy questions to ask. How are the data collected? I never know whether data is singular or plural. I always grew up data were plural, and then I got involved in journalism, and I was told data is singular. So I don't know. I think that maybe even journalists are not all in agreement over this. Is there room for bias? This is what? Sorry?
It's GIF.
Oh,
Sorry, inside joke.
GIF versus GIF.
Okay, got it. All right. So surveys are a really important place to look for those kind of bias. How are questions asked? You will find, if you did a survey on what people think about abortion rights, pro-life, or you will find like 80% of Americans will say that they're pro-life, but 80% of Americans will say that they support abortion in certain circumstances. It's all a matter of how you ask a question. So surveys are really important on doing that. Food studies are also, this is one of those things that comes up with cancer. It's why I did the nuts thing. Like, if you ask about what people eat, how carefully are they reporting it? Are you asking them to remember what they ate like far in the past? How are you designing your study? What kinds of data could come in? Are the data biologically relevant? I only put this up because there's always a study about how, like, if you have the ratio of the length of the third finger to the length of the second finger is greater than some amount, you're inclined to be violent. I mean, there's these sort of crazy studies that suggest
That's not true?
there is some evidence that there's true, but of course it's obviously completely silly. In fact, one of that's coming up. It has to do with multiple testing, and I'm going to get to that because it's actually interesting. Why would they see this result if it's not true? And I'll talk about that. Are the numbers significant? So a statistical significance has a very specific meaning, which I'm hoping to get to in this talk. And again, the scientific articles are usually trying to get at something really specific, is there increased death associated with eating red meat is a perfect example. And the point about this is that if you ask a question like that, are you considering other explanations of that? And it's a really important thing because in the design of a study, you can say, well, red meat eaters also are more inclined to smoke. They're also more inclined to drink alcohol. They may also have other behavioral things that are cancer risks. So how are they dealing with that question to know whether to attribute a risk to eating red meat or to other behavioral things that may themselves be risks for cancer? Now, this can be a subtle issue because sometimes the thing that's being considered is what's called in the causal pathway, which is to say if red meat leads you to smoking, then even if the smoking caused the cancer, the red meat should hold partial responsibility for it because it led to that. In the case of red meat, that's a hard sell, but there are others that are, especially when it comes to obesity and diabetes and other things, where do we attribute the cancer risk is a difficult question. Okay. So I think I mentioned these things about how people are recruited. looking at that. And so again, just reading the methods section of how they collected data can be very useful. You can skim the statistical analysis part and still get something very useful out of reading the actual study. Okay, so this slide about moral and statistical collision is one I just like to share this because there are so many topics that are in the news, and all of you are for the most part health reporters, if not actually just talking about cancer. And I wanted to kind of point out that we have all of these moral sort of perceptions, and they really do hugely influence how we report on things and how we design research studies. So this is not something that like journalists have their axe to grind, which journalists do, but so do scientists. So it's not that there's sort of this objective world out there that's being reported by you. It's that there's a lot of bias in all places around surrounding these kinds of research, and it's hardly ever do I see someone who's doing research on social topics without, like, you could look up the author and know what they think beforehand. Okay, so it's really important, therefore, to kind of recognize those biases and understand how it is that we come to the table when we ask these questions. The medical abortion one is one of my favorites because it's such a hot topic, and usually you'll have newspaper articles that say somebody took the RU86 pill and died. And then you'll have a reporter who says, this pro-life advocate points out that women are dying because of this medication and it should be banned. And then they will find a pro-life person who says, millions of women take this drug safely. And no one's admitting what's underneath, which is, what's the risk if I take this drug? Okay, so that's the question, right? From a medical point of view, let's take away the evaluation of the moral part. But everyone's being a little bit disingenuous because the pro-life person is not really concerned about the few women who died from taking the pill. They're concerned about the many babies that died. And the pro-choice person is not not only thinking about how many people took it safely, they're thinking about important quality of life issues that are related to the accessibility of abortion. So neither side is saying what they really think, and the journalist's job is to say, what is the risk? And not just what's the absolute risk, but can I compare that risk to a woman's decision to have a child, which for poor people in the United States, it's about 10 in 100,000 women die of childbirth, which is, by the way, higher than the percentage of dying due to this drug. What about a surgical abortion? How does that compare, as opposed to, say, a pill? So those are questions that I think really make the conversation a lot more productive and move away from the moral judgments whether it should or should not be accessible, which is kind of a different question. Or one could include that point of view as well, but it's certainly, I hardly ever see someone actually report on the risks. But all of these things kind of tend to bring out a certain level of, I got an opinion, I want to share it. All right, crime. Okay, so this is just a cute little slide about causation versus correlation. And in fact, how difficult it is really to tease it out, because obviously a statistics class helps you with your statistics, but okay, or with deciphering these, I suppose. All right. So as I said, it's easy to be fooled. Here are a few cool things. Height correlates with reading skills in children under 10. Now, what is that about, right? That's about the fact that as we grow, we also learn to read. Income correlates with success in college. Well, that's a very interesting one, and a big question about causation is that because poor people have poor preparation, or because they're worried about money while in college, or something else going on. I've mentioned this ratio of finger lengths correlating with aggression. I don't believe that's a real one. Facebook correlates with poor grades. Yeah, but I read another study that found that Facebook correlates with good grades, and what it's about is what you're using it for. Is it your network to find support amongst your classmates for your work, or is it your distraction, your way of getting away from your schoolwork? Doing heroin correlates with doing marijuana. Higher taxes correlate with high annual growth, inversely correlated with poverty rates. Alcoholism correlates with less gray matter in the prefrontal cortex. That last one is probably causal, right? There's sort of like good mechanistic things. The second to last one, lots of discussion of the mechanisms behind it and the delay involved with economic blah, blah, blah. Okay, so there's like big questions, and I think the key thing is to always really question whether you've got when you have a correlation, whether you've got something causal going on. Here was a cute example of this. Various fMRI studies. That's this big magnet you could see over here on the right where people go in and then they go through some activity while they're in the machine, and various blood pattern activities in the brain are being measured. So our blood flow has certain magnetic properties that can be picked up, and then using a statistical analysis you can actually tell which parts of our brains are becoming active, though it's not clear what we're doing with that activity. Okay, so the typical study, you see some pattern of blood flow in the brain when some tested behavior occurs, and we of course assume that it's due to it. And this is where you'll get studies like playing video games lights up the same part of your brain as addiction. Okay? So now where are biases coming in? Guess what? So does having sex, so does gambling, so does buying something at the store. So we've got to really be careful to kind of tease that out. I want to point out a couple of these things. There's lying is one of the big ones. Lie detector tests were all over the 1980s. I don't know, some of you are younger. But, it was kind of like the big sort of dream that we could tell when a criminal was a criminal just by asking him while he's on a lie detector test. And then they realized, it's really like, not that reliable because people get nervous and they have all sorts of physiological responses that are similar to what we experience when we lie. Well, guess what? Same could be true going on with fMRI, but nobody brings that up. It's sort of surprising. It's like suddenly it's like the newest, greatest technology to tell if people are lying. And they have all sorts of, I won't go into violent video gaming leads to violent brain patterns. That's another one. Of course, it could be that when we fantasize about violent things, we are engaging in similar kind of brain patterns. And how to tease that out is often not done. So you have to read the study to see, did they consider that maybe that's all that's going on? This is my favorite. Math anxiety triggers activity in the pain center of the brain, right? This was a year or two ago. This thing came out.
That's totally true.
And but the thing is, no one actually experienced any pain. So really what they did was they compared people who suffer from math anxiety with people doing crossword puzzles. I would like them to have people who suffer from math anxiety compared to people who suffer from crossword puzzle anxiety. Because I want to tease out whether it's the math or the anxiety. What I suspect that they measured was an experience of anxiety that's going through our pain centers. And I have no doubt that math anxiety exists, if you were wondering whether I believe in it or not. I totally believe in it. But I don't think that that's really what's measured here. But it really gets a lot of good press because it hurts. Okay, and nobody experienced any pain at all. So it's interesting also that anxiety, if it is, or whether it's math, is lighting up pain centers in our brain is already kind of an interesting thing about that pain center not being specific to pain. Okay, so let me kind of just say a couple words about how much time did I have? You said till 3:45?
You have 75 minutes from whenever you start.
Okay, great. I don't want to kind of talk the whole time, but I just wanted to...
Absolute.
Right.
3:45 was...
3:45. Okay, great. So when you have a correlation and you think it could look like something is causing the other, the big thing to look for are what are called confounders. And confounders are those things that get in the way of measuring something appropriately. And I'm going to give you a pretty heated example where I'm not going to come down on one side or the other as to whether there was confounding, but only to point out that the data suggests that there might have been something going on, which is the relationship between babies dying in their first year of birth and being breastfed or not being breastfed. And there's been a huge amount of discussion in the media about this and a huge amount of scientific data about this. And one of the things that's really hard, really the hardest thing to do about this is that the best we can do to ask this question is to look at what are called observational studies, where we take groups of people who have already made their decisions about what they're going to do, and we watch them over time and we see what happens to their children. Or we could take a look at families where a child has died and compare them to families where children haven't died, and we could ask questions like that. But never can we set up what's called an experiment, where we say, this group of people will breastfeed, this group of people won't, let's see what happens. So we end up with the fact that different people make different decisions. And all sorts of things have been said about breastfeeding. It used to be that breastfeeding increased your IQ. Turned out they didn't control for the confounder of the mother's IQ. Oops. So people with higher IQ were breastfeeding more, and they were attributing the benefit of IQ to the children to breastfeeding, and it may well have been either a biological benefit or a genetic benefit or even a social benefit that came from living in a household with high IQ people. And I don't want to go into that question, but it's not clear at all that it was a breastfeeding benefit. There have been all sorts of things attributed to breastfeeding that have crazy questions of confounding, including for a long time the studies not including confounding for smoking, which is sort of a crazy obvious risk to a child. So these are the kinds of things I think are really, really important, and I'm going to throw up a slide later on that'll stoke that fire a little bit more and hear what you have to say about it. So when can you think, okay, I've got these observational studies and I really want to know if I have something that's causal? Well, the main thing is, are the statistics overwhelming? Are they observed in many contexts? Do you see repeated tests showing the same effect on different groups of people? And do you have any double-blind case control studies? So, studies where nobody knows who's in the, one group or another. And that's the kind of studies that are done in order to approve medicines, which have their own problems at times if not done properly, but or if there are too many interests involved. But I think these are the kinds of things that we see when we say smoking causes cancer. We don't have double-blind case control studies, but we have all three of the others. We have really overwhelming evidence that comes from many different sources on many different groups of people. So that's something to keep in mind, that we have to be really careful in making those causal assumptions. And of course, what we're always trying to do is measure small effects. And that's where it's always really hard to do, because smoking has such a large effect that it was somehow a lot easier to get a lot more vested interest maybe in keeping that information unavailable to people for a long time. All right, so one of the big things that people talk about all the time is called a p-value. How many of you heard of the p-value? All right, so the p-value is, how many of you did not hear, have never heard of the p-value? Okay, so you'll see in a lot of medical studies, they'll say this was statistically significant with p less than 0.05. And there's a question of, as a starting point, what do we mean by that? And in order to explain what we mean by that, I'm just going to give you a little sort of brief foray into probability. So if you flip a coin, you get either heads or tails. I'm just going to assume it's half heads, half tails. And when you flip that coin, if you flipped it many, many times and you always got heads, you'd probably think there's something wrong with your coin. And that's a sort of subjective, just sort of opinion that, like, well, roughly speaking, it should be half and half. Half the coins should be head, half the coins are tails. But you know what? If I flipped it 10 times and 6 were heads, 5 and 4 were tails, I probably wouldn't think it's a big deal. 7 heads, 3 tails, well, maybe, 1 head and 9 tails, I might think there's a problem, okay? So we can evaluate what this means to be a problem by calculating the probability of getting 9 tails and 1 head. What's the probability of seeing this sort of extreme data? And the p-value is a measure of the probability of seeing the data that we see, assuming that there's no bias involved. So when we make the assumption that the coin is fair, that's the only way we can then calculate what the probability should be for getting 9 heads, 9 tails, and 1 head. We can't assess that probability unless we can make an assumption about what it is. So we'd say it's going to be half and half, then we calculate that probability. If it's really small, we say, well, then it's pretty unlikely that was a fair coin. That's the process. You assume it's fair, then you check what's the probability of seeing the data you see, and then you reject the notion that it's fair based on what that probability is. if the probability is really small. So that's kind of the idea. It's a 3-step thing. Now, the way that this is called, the first step where you say, I'm going to assume the coin is fair, that's called a null hypothesis. The word null makes it think negative, and it's what makes it so confusing for what I will say in a few minutes, because there's a negative of a negative. But the starting point, the null hypothesis is, there's no difference between the two groups of people I'm looking at. There's no difference between the probability of getting a head or a tail, or that everything is fair and square. There's no influencing factors. Usually you're assuming there is no thing that is what you're actually trying to prove exists. Okay, that's the assumption. It's called the null hypothesis. Then you say, now I'm going to flip my coin a whole bunch of times, and I'm going to see what data I get. That says I'm going to run my experiment and see what my data are. Do people on this cancer drug get better or die? And I'm going to compare it to the people not on this cancer drug. My assumption is the cancer drug does nothing. And now I'm going to see, now I have some data. Some people got better and some died in the first group. Some people got better and some died in the second group. And I can say under the assumption that there was no benefit at all for taking this medication, what are the proportions that I'm seeing? Are they what I expect? So what do we mean by what I expect? The probability of seeing that data is at least 5%. At least 5% probability of seeing that data. That's the measurement that the community has agreed on. It's an arbitrary cutoff. The lower your p-value, which is to say the less likely something is to occur, the more strongly you can say, aha, that coin was biased. So the p-value, when you say p is less than 0.05, the 0.05 is a probability. It's saying with a 5% or less chance I would have been to see this data. And because that's a really small chance of seeing the data, you say I'm going to reject the null hypothesis. So you reject the hypothesis that the coin was fair, and you accept the possibility that the coin was not fair. Okay, so that's the way it goes. It's a 3-step process. You assume it's fair, you collect your data, you do a test to see what likelihood you would to see that data, and if it's not very likely to see that data, you reject the idea that the coin was fair. Okay, so just to give you a sense of this, if I flipped 1,000 times, I just calculated some probability here for fun, you get 520 heads, then that would be like under 10% chance of getting that many heads or more, and you always have to kind of like say this or more thing, right? Because if I got 520 or 521 or 530 or 550, they're all kind of skewing in the same direction, right? So on the other hand, if I had 550 flips that were heads, then that's actually much, much more unlikely, and the chance of that happening randomly is only about 0.1%. That's a very low, that's like 1 in 1,000. Okay, so that p-value is 2 decimals over from that, 0.001. And that's saying you probably have a biased coin if you flipped your coin 1,000 times and got 550 heads. Can it happen? Yes, it can happen. But it's just not very likely to happen. So we reject the idea that the coin is fair.
So the higher the p-value, the more you can trust or not trust.
Okay, well, so what's the question of what you're going to trust? So the higher the p-value, the less sure you could be that the data are anomalous under the assumption that they came about randomly. So the less you can reject the idea that there was a difference in your two groups. So you're going to assume your two groups are the same. And if you get like p is 0.8, means, well, pretty likely they are the same group. If you get p equals 0.05, you're like, well, gee, that's really unlikely to see these data. And so if it goes lower, the smaller p gets, the more likely, the more sure you can be in rejecting the idea that the groups are the same, which is to say the groups are different. So if you're looking at an interesting study I was just looking at recently, had to do with autism and vaccination, and you say, what are the rate, you'd like to know the rates of autistic kids amongst vaccinated versus unvaccinated people. That data is not widely available. What you can do is look at the rates of vaccination among autistic kids, and this kind of gets to this question that you guys brought up earlier of what are called odds ratios and what sort of ratios can you get at? But if you say, look, among vaccinated kids, I see 1%, 1.5% autism rates. Among unvaccinated kids, I see 1%. How do I tell whether that's a true difference that I might want to attribute to vaccination, or at least consider the possibility that vaccination is coming into play, and how much of that difference is because the data just came out that way, because there's a certain amount of randomness in our lives? And the answer to that question is you have to do a calculation involving how many people were in the study, how many, how much data you have. The more information you have, the more coin flips you have, the better you can ascertain that. Like, meaning that the smaller differences are more meaningful if you have lots and lots and lots of people. But when you're trying to ask whether that question is meaningful or not, that's the question you're asking. What's the probability of seeing that data if vaccination didn't matter? And if that probability is really small, you reject the idea that vaccination didn't matter, and you say it does correlate. Okay, that's the steps. Does that make sense?
So
Okay.
is this
Yeah.
a tool for evaluating the legitimacy of your control group? Or is it a tool
Not
for
at all.
evaluating the results of the study?
Results of the study.
Okay, so since I'm kind of following this today, but
Yeah.
I'm not going to remember it tomorrow,
Yeah.
what are we looking for in a p-value?
What you're looking for, no, that's great. That's exactly right. So what you're doing, what you want to look for, and I'm gonna do an example in a few minutes. But you're looking to say, my p-value was below a certain threshold. The typical accepted standard in the biomedical community has been 0.05. So one thing you'll see is people saying things like p equals 0.1, which is not below 0.05, and saying with a trend towards statistical significance. It's really misleading. It's not statistically significant by the agreement of the community. But what I want to emphasize to you is that it is an arbitrary cutoff. There are things that happen that are rare that happen, and maybe 0.05 is too high a threshold. We should be asking for 0.001. Like, our data should really, really, really reject the idea that the two groups are the same. Or you could say the other way, well, wait, there's a lot of really interesting things that could be going on. We don't want to lose track of all the possible things that might be causing us health problems. So let's make our threshold 0.1. Meaning if the data are different, and there's a 10% chance that could happen by chance, but that's still not that likely, so we should consider those things. So it's an arbitrary decision. So the medical community, for the most part, has agreed on 0.05. So if you see p less than 0.05, that suggests statistical significance. But what I want to emphasize to you is that is a statement about the likelihood of seeing those data. It's not a statement about true or false. It's not a binary. It's not like, yes, that means that, nuts save lives. And it's not either going to tell you that it doesn't. It's sort of just evidence. And it's on a continuum. So the less likely you are to see the data if the coin were fair, the more you're likely to say, that coin wasn't fair, meaning my two groups are really different. Say, like vaccination and unvaccinated groups are really different if I'm unlikely to see these autism rates.
So if someone is, I'm sorry.
I was going to say, are we only likely to find articles with p-value of 0.05 or less in peer-reviewed published journal articles? I mean, can
Yes,
we
you're
assume
you.
that if it's peer-reviewed?
If it's a peer-reviewed published, I have seen at times, I have seen a fair number of things, but probably still under 10% of the things I've seen, where people try to argue statistical significance at the level of 0.1. And I have seen, so sometimes it gets published anyway. In fact, I wish a little bit more that journal articles were more open to results that aren't statistically significant, because I think that they still tell us something, and it doesn't reach that critical threshold, but it also doesn't make it true if it does. And that's one of the things that we see, like so many mistakes or irreproducible work, because even there, we just said there's a 5% chance of seeing that data. Well, lots of things happen in the 5% range. So, yeah, but that doesn't mean it couldn't happen that way. So you'd like to see more evidence still. It's maybe like a good precursor to then have more work. And one of the things that I'll talk about here is also like the big importance of putting our work in context. So, one study can just by chance hit upon something. And in fact, there's a lot of statistical tools they can do to make sure they hit upon something. And I'm going to talk about that because it's a real key thing that you guys understand what all the tricks of the trade are. So let me just go on to the next slide. And this is just a picture to kind of like show you what we mean by this 5% threshold. Okay, so here, this is a normal curve, also called the bell curve, although that's apparently going out of fashion. And the idea of this is that a lot of phenomena that we see in a regular way happen with probabilities that are distributed according to this curve. So one of the things that you should get out of is that, like, most times if you were, so the thing you should get out of this, the normal curve is a good approximation for coin flips when you flip many coins. That's a big theorem in statistics. And so if you said, okay, I'm going to flip a bunch of coins, and if I got right in that middle point, like I flip 1,000 times, I got 500, then I'm in that little blue shaded region. It's saying, well, there's a 68% blue shaded region that I'm going to get greater than this value of heads and less than that value of heads. And these are things that can be computed. What is mu is the average, this sigma is a standard deviation. So these are all things that kind of quantify probabilities. So we think of probabilities as like these great unknowns, but as a matter of fact, we can quantify how well we know something, and that's a huge amount of what statistics are doing. They're not telling you we know. They're telling probably you wouldn't see this if not. That's what they're telling you. So these kinds of pictures are saying, well, I expect 68% of the time to be in that middle group, and I expect between where the 13.6 and 13.6, all from the left of the first 13.6 to the right of the second 13.6, that's just over 95% of the data. So that's where you expect most times if you take 1,000 coin flips and you flip them, most of the time the number of heads you'll get is in that range. But 5% of the time, a little bit less than 5% of the time, you will be in that yellow region. All right, outside of what you expect. And that's what they're telling you when they say p less than 0.05. They're saying you're in the yellow range. It's really unlikely. All right, these data are unlikely. So what you do is when you say it's unlikely, so I'm going to remove the hypothesis I started with, which is that all I was doing was flipping a coin. I'm going to say there's something else going on here. And that's what a lot of research is saying. There's something else going on. And usually there's a correlation with this and that. All right, so here is, let's see, this is the one on breastfeeding that I wanted to show you, but I thought I had it with some red circles on it. I think my red circles didn't come up. All right, so I'll have to point this out to you, and it's a little bit blurry, unfortunately. So this was actually taken from a big study on breastfeeding from a few years ago, so I'm not up on the most recent research, so I don't want to say this is sort of the be-all and end-all, but I wanted to point out to you what they're doing is they're saying, okay, I'm going to measure amongst women who ever breastfed versus those who never breastfed, what's the percentage of, what's the relative risk of having a child die under 1 year old. Okay, so it's a horribly sad thing to look at, but a really important thing from a public health point of view. And what they're doing is they're dividing, let's see, these are called odds ratios. Actually, what they did, let me restate what they did. They took the kids who did die, and they asked whether they were ever breastfed or never breastfed. Okay, so they took if they've ever breastfed and they divided it by never breastfed. They found, if you look at this under, they didn't actually report the odds ratio in this table right here, but this 0.76, that is the odds ratio. Sorry, they did report it, but then they give you this confidence interval. And that confidence interval is an interval over where if you were to redo the study, you should expect 95% of the time to get in that same range of values. So when a confidence interval does not contain 1, the number 1.0, that's when you say there's something going on. You reject the hypothesis that these two groups of kids were the same. And so you see that this 0.76 with a parentheses confidence interval of 0.65 to 0.88 is telling you that if you were ever breastfed, you're less likely to die as a child under 1 year old than if you've never been breastfed. So it's kind of like one of those things that you really want to know. But then they did these studies in which they said, well, let's look at, this Sudan adjusted. These are just two different studies. But you start looking at what happens if you break up the data into individual parts. And I want to point out specifically the death cause specific ways of dying. So how did the child die? Because a lot of people say, well, SIDS or immune response. And if you look in this column right here, you see all of these numbers are less than 1, suggesting for all of them there's a protective effect of breastfeeding. But there's, in the confidence interval, which is where you can be 95% confident, so this is very symmetric to the p-value, where you say, how sure can I be that if I were to do this again, I'm not just getting an anomalous result, that 95% of the time I would see it again. And there's only one category in which the confidence interval does not contain 1. So this is the one category which is statistically significant, and it corresponds to injuries. So in other words, the only thing that's statistically significant is that children dying by injuries have a protective effect due to breastfeeding, which is very different than what I think most people's conceptions are. Now, other things trend toward significance. The odds ratios are still less than 1. But the first thing that this poses in my mind is, are there confounding factors about care of children that impact their lives that are themselves correlated with nursing or not nursing? Or is it possible, so for example, here's a confounding factor you could never really control for is abuse, right? There are plenty of people who abuse their babies. It does happen. These are rare events, as are babies dying. Are we not controlling for that? And those are deaths that are getting attributed to injuries. And those are also women who are less likely to breastfeed, but it has nothing to do with the breastfeeding. Are there situations in which, well, actually, it's really the importance really has to do with holding the baby close, and there's a mechanistic thing involved, in which case you better not tell women you can pump and go to work. You better tell them your child is at greater risk of injury unless you stay home and physically you nurse your child. Those are really different messages, and I think these are the kinds of things that when you actually can open a study and say, well, where are we seeing the significance, you can have a different conversation than you might have if you just buy into, yes, it's statistically significant, and they controlled for smoking and mother's education and other things that they could control for. They can't control for things like depression or quality of care. Okay, they can't. It's just impossible. So there's these big questions about how are you going to, or maybe you could say they could, but they didn't do it entirely well, or there's some other way, study design. So there are these big questions of how do you conduct a study that shed some doubt on the results. And when I saw this result, that was the first time that I really myself felt like I wasn't clear any longer what was going on, because whatever might be impacting injuries may also be impacting other categories and that sense of the trend toward benefit. Yes?
I totally understand this thing that the confidence interval will indicate whether you should even put any faith in the results. But okay, so let's look at the one statistically significant result here. And I deal with these odds ratios all the time, and I'm like, well, what does that mean?
Right.
Because again, you're not comparing one group to another, you're comparing one group to the likelihood, or tell me exactly
what is an odds ratio?
And if you were a reporter, you'd say your risk of blah, blah, blah is greater than blah, blah, blah.
Right. So the correct statement in this case is, let's see, just to make sure I could get this right for this particular one, percentage of ever breastfed versus Odds ratios for post-natal analysis. Okay, so I mean, of course, here I just clipped something from a study, and I don't have like the whole study, so I want to be careful to not say something actually incorrect in this circumstance. But what I think that they did, yeah, let me bring it up on a different example, because what I'm afraid of is I'm going to say something that's not actually what they did in this case. But in general, what you want to do is say that the odds of X. So what's the difference in odds and relative risk? Maybe as part of what you're asking. Okay, so this is saying there's a, in this case, 40%, 41% reduction in odds. I believe it's saying of dying due to, of dying in the first year if you breastfeed compared to if you don't. But it's a reduction in odds, not in relative risk. This doesn't have anything about your risk of dying in your first year of life. Okay, it doesn't have anything about it. So in general, what an odds ratio is a ratio of odds. What are odds? Odds are, it's like when you go bet on a horse. It's the chance of winning divided by the chance of losing, or the chance of losing divided by the chance of winning, depending on which way you do it. So a risk, when you talk about relative risk, we're talking about, say, a risk of group 1 divided by risk of group 2. For the risk of group 1, you use the absolute risk. It's the absolute risk of group 1 divided by the absolute risk of group 2. That's relative risk. If I say odds, it's really different. I don't know your actual risk. I know your well, if I did know your risk, what I would do is I would say the risk of it happening divided by the risk of it not happening, rather than just the risk of it happening.
You see why reporters make a lot of
It's very easy. And I didn't actually put on my slides any fractions, but there are the fractions that you're calculating. Odds are like, if my odds are 1 to 7, my probability of winning is 1 in 8. Because it's 1 win for 7 losses. That's what odds are. 1 win for 7 losses. But my actual probability of winning is 1 in 8. Out of 8 times, I will win once and lose 7 times. Okay, so that's why it's different. Now what happens is odds ratios are very close to relative risks when you're dealing with small probabilities. That's why people might use it for something like this, where you're talking about something that's a rare occurrence. Like, it's not like 10% of babies die, right? It's a really small percentage of babies that die. That's why you talk about it when you're dealing with what are called case control studies, where you've got your cases. You don't know the actual probabilities, but you have a group of people who suffer from something, and a group that you call controls who don't suffer from something. So they're close as long as the thing you're talking about has a really small probability. But technically speaking, you're not talking about increased or decreased risk. You're talking about increased or decreased odds. So if you just use the word odds instead of risk, you're going to be right. Like this is saying a 41% reduction in odds.
Now, where are you seeing
But
41%?
just because
I'm
it's,
looking- I'm trying to
yeah, no, that's fine. Because this is
Pointing it back.
0.59.
Okay.
And so 0.59 means that one group was 59% as
So
likely
if you were just
as the
doing
other.
it off of the total on the first.
Yeah, if you were going here, you would
column,
see 21%.
21%.
That's right. And
You
that's
could say-
statistically significant.
As a reporter, you could write, women who ever breastfeed are 20, or children of women who ever breastfed, or children who were breastfed. Are
Had 21% reduced
less
odds.
likely
No,
to-
reduced odds.
Reduced odds,
Mhm.
not less likely.
That's right. That's because likely is usually referencing, but you wouldn't be off if, in terms of like the math, it would only be a little bit different because that's a very rare event. But
Okay.
that's not what the study said. The study said 21% reduced odds.
Okay, so odds.
Yes.
All right.
So it's an odd statement, but again, it's not, I mean, this is a, and in that case, the point, I think what I would suggest is, if I were looking at this, I would say this result was statistically significant, and in particular was driven by the one specific cause of death that was statistically significant, which is injury. And that really tells a very different story, which isn't to say that the other ones don't have some relevance here. I think that they're interesting things to ask about. Mechanistically, though, I'd want to know what's going on with injury. So that was my kind of like, oh, I did have it circled. See that? Okay. So the point here, though, is that when you see a confidence interval that doesn't include 1, it's the same idea as saying your p-value is less than 0.05. The 95% confidence interval is a statistically designed trick to measure the likelihood that if you were to conduct the study again, you would get similar value to what you just saw. Okay, so it's structured that way to measure that. So if so having something that's statistically significant says something's going on. All right. Now, I wanted to make a mention about something called multiple testing. And this is something that so many scientists engage in, I can't even tell you. Okay? And here's the idea. We just said that if something was only 5% likely to occur, we could get a paper out of it, right? We could publish it. And we also said that, like, journals don't like to publish articles that aren't statistically significant. So we really want that 0.05, right? We really want it. So now suppose I have a lot of data. I have a lot of data about violent, aggressive people, and I have a lot of data about various body measurements of theirs, like lengths of fingers and things like this. And I really want a study that's going to show me that there's some predictor for violent behavior. Well, let's see. I might say let's measure how long their nose is and divide that by the radius of their ear. Oh, that didn't work out. Well, let me test 5% shot. That didn't work out for me. Well, I'm going to measure the length of this finger and divide it by the length of that finger. Well, that didn't work out. What if I try this finger and divide it by this one? Okay, so you can imagine what I'm doing. I'm throwing my dice each time. And, well, I just have a data set. I don't have everyone in the world. I have a data set in which I've got all these measurements. If I keep throwing my dice, I will find, with 5% probability, something that's 5% or less likely to happen. So all I have to do is do this a bunch of times, and I'm going to find something that looks statistically significant. And then what I can do is I can report on that and not bother mentioning that I checked these other things. All right? And all of a sudden, I have this great study. I have a cartoon about this. I got to show you my cartoon because it's real cute. If I can, I keep forgetting where. Okay, all right, here we go. So these are experiments. We found a link between purple jelly beans and acne, p greater than 0.05. That means that link was not really rare data. Okay, so they go through and they say, well, let's try the brown jelly beans. Well, what about the pink ones? Blue ones, teal ones? Okay, you kind of get the point, right? They're trying a whole lot of different colors and trying to see if those people who are eating more of those colors were getting more acne. And they go through, and then they try a bunch more colors. We've got mauve and, orange, and somewhere in there, let's see where it was, the green ones, the fourth one up there on the top, right? Did you see that p less than 0.05? Mm-hmm. All right, great. So now, oops, there we are. We get it in the news. So that's called multiple testing. Now, there are kind of two different ways in which you can do multiple testing. You can try different, this is sort of the main thing that people do. They sort of take different parts of the data, splice it up in different ways. So how do you avoid being fooled by this? One of the key things is whether the questions that were asked were specified before you begin the study. That's the key thing. If you say, I'm going to do a test for purple and mauve and green and blue and all these different jelly beans, a good statistician would say, well, now you need to adjust for multiple testing. There are things that you do that change what that p-value will be to be valid. And you have to make those changes. You have to adjust for the multiple testing. So we don't need to worry about how that's done, but you can ask the question, was that done? Now, the question of not reporting all the things that you did that you didn't want, that didn't make it statistically significant, that's something that, unfortunately, it's really hard to know whether someone did it, and they're supposed to say. So really good journals actually have a list by which authors are supposed to comply, in which they say what they did, all the tests that they did. They say everything that they did so that you know. But the key things are were the questions that were asked designed before the authors saw the data? Because guess what? If I looked at the data beforehand, I don't even need to go through all these multiple tests, right? I can just pick out the green ones. I know they're the worst, right? And now I got it. Green. That's it. How would you verify that green jelly beans cause acne? Is you would do another test with totally independent data. How can you do that if you only have some data? Well, there are tricks. Like you could use half your data to generate hypotheses and the other half to verify your hypotheses. So there are ways of doing this, but they have to think that people who design the study have to think about that, and you need to ask. This is especially important when it comes to food studies. I've seen so many food studies. These people are just looking through that data till they see something that they think will be good, and then they run their tests, and then they say, yeah, it's good, and it's like, well, right, but what did you look at before you know? If you only look for it first, what that tells you is maybe that's a good thing to look at. Certainly things that are bad for you will come up in that way, but so will a lot of things that are just statistical anomalies. So that's one of the things that's really important about understanding this idea of what a p-value is the probability of seeing the data. So if you run it lots of times, you have a pretty high probability that you'll see something that has a p-value of less than 0.05. And actually people have studied that probability. You may have seen some work by an author whose name is, I think it's Ioannis. Yeah, Ioannis, who's done a lot of work on why it is that so much scientific research is wrong, and actually how you can guarantee that some of it's wrong, probabilistically speaking. Okay. So I'm actually going to move ahead because we only have a few minutes left, and I'm not going to talk about patterns of coins. This is sort of my last section, but just a couple metaphors for bad statistics. One is what's called the Texas sharpshooter fallacy. So here's how it goes. Your friend takes you by the barn side and says, I'm a great shot, let me show you. And he busts up with his gun like a whole lot of places all over the barn. And you look at it and say, well, you're not that good at all. You're like completely off. And he says, no, I am. There's my bullseye. And boy, he looks pretty good if he draws a bullseye afterwards. And that's actually like a really kind of clear thing you do where you sort of collect a lot of stuff and then you look for something and then you say, you see, I got it. And you have to be a little careful with that. We talked about absolute versus relative risk. My advice to you, be a skeptic at all times. And let's see. I think I mentioned all of these things here, but a little bit more slowly than in these slides. And I can stop there, but we have a few minutes left, and I have kind of two options what we can do with this time. I'm either happy to answer your questions, or I brought like a study that was on association of nut consumption with total and cause-specific mortality that we could go through as a kind of example. How could you read it? And we could do that. And I don't know what. Did it? Yeah, okay. So I'll just pass these on. I'll just keep one for myself.
Can I ask a question while we're passing?
Yeah, sure.
And go easy on me, please.
Yeah.
But I was doing a report on cancer rates, and when I was looking at the information, I saw a number per 100,000, and I put that in my article, and my editor emailed me and said, can you make this into a percentage? I said, absolutely not.
Okay.
How do you do that?
Right. Okay, great question. So you take your number in a calculator, you take your number and you divide it by 100,000. Okay?
The number divided by 100,000.
That's what's called a proportion. Then you multiply that by 100, and that's your percentage. That's it.
Are you kidding? Is that simple?
That's simple.
Are you kidding?
No. That's simple. So if it's like 1 in 10, right? We know 1 in 10 is 10%, right? But let's just say we didn't know that. So 1 in 10 people die. You would put in 1 divided by 10 in your calculator. You'd get 0.1. You multiply 0.1 by 100 in your calculator, so you don't do it in your head, but that just moves the decimal over 2, and that'll give you 10%. So anytime. 5 in 100 we know is 5%, right? But we take 5 divided by 100 in our calculator, we get 0.05. Multiply by 100, it'll move the decimal point over 2, be 5%.
We could do a whole session on math for journalists. Like stuff like that.
Yeah, that would be. That would be awesome. I'd love to do that.
Suzanne, did you say no one would attend?
Okay, cool. So just to kind of, we only have a few minutes. So it kind of, just starting out with this, these people were looking for whether there's an association between nut consumption and subsequent total and cause-specific mortality. Now, the data that they got were from 2 different studies involving women in the nurses' health study and men in the health professional follow-up study. Now, just a comment that these are sort of highly used studies of observational studies of people and their eating patterns, because these health professionals were really careful to record it, and they did a better job than the average population does at recording what they ate, because they're health professionals. So if we just look at the results, which is the abstract, right? It says the pooled multivariate hazard ratios for death among participants who ate nuts as compared to those who were not were 0.93, 95% confidence interval 0.90 to 0.96 for the consumption of nuts less than once per week. So just as a starting point, what that means is that they found that the rate of dying was 93% as great if you ate nuts compared to if you didn't. So there's a rate of dying if you don't eat nuts at all, and that rate is lower if you do eat nuts. So it's saying that you're less likely to die.
By 7%.
By 7%. Now, this hazard ratio is a slightly complicated thing. It's a little bit different than rate. So when we talk about like relative risk, you'd be measuring everyone who died. If you talk about hazard ratios, you're talking about everyone who died in a period of time. So it's just a slightly different thing, but it's certainly valid to simply talk about risk without specifying which kind in this context. So they're saying that if you compare those people who ate nuts once per week, they're 93% less as likely to die as compared to those people who ate once per week. That confidence interval, notice, does not contain 1.0. So that's telling you that this is a real effect. Now, does it tell you it's due to the nuts? Absolutely not. There are a lot of things that could correlate with eating nuts, but it is telling you that the nut eaters were less likely to die. And the interesting thing, if you look at what they then do afterwards, is they say, well, what if you eat more than 2 to 4 times per week you eat nuts? And it went down to 89.89, which is to say that if you compare people who eat nuts 2 to 4 times a week to those who eat nuts not at all, your rate of dying is 89% compared to those others. So you're less likely to die. Okay? So that's what they're talking about. But if you said, well, how do we get something more interesting? Like, why do I say don't only read the abstract? Let's jump to the conclusion, because great, that's what their results were. And if we jump to the conclusions or the discussion, which starts on page 2008, it really goes into 2009. They talked to you first of all with saying they had their results were consistent with findings of other studies. So that's actually really important. You can contextualize this, that it's not just one study that's saying nuts are healthy or are correlated with living longer, but other studies as well. But then they say also, if you look at the second paragraph on page 2009, several explanations for our findings are possible. And here's where you get the questions that you should be asking about the study. The observed associations could reflect confounding by unmeasured or poorly measured variables. So in other words, there could be other things going on that correlate with nuts. And in fact, if you read this, they do worry about the fact that nut eaters exercise more, they eat more fruits and vegetables, they have other healthy behaviors that could explain that reduction, and they tried to control for it, and that's part of what reading the full study kind of shows you, that they did think, well, wait a second, what might it not be nuts? And they give you good evidence that nuts really could play a role, but they also maybe bring up other questions for you, depending on how much you're snooping around about it, like, well, wait a second, what about sleep patterns? Maybe sleep patterns make a difference. And there's never something that you can do that's going to give you 100% surefire answer. So I think that your job is to kind of say, how strong is what we're seeing? Like, are these results in the context of other results showing similar things? Are we able to sort of tease out some obvious confounders like exercise or fruits and vegetables? But they basically say here, we just don't know about everything, which is not maybe the most interesting explanation. But the other one was this reverse causality being another thing, where it's not that eating nuts reduces your mortality, but if you're someone who's not dying, you're more likely to eat nuts. And that's actually an interesting question. Like, if you have chronic health problems, maybe you're not going to eat nuts for whatever reason. And, of course, that is something people do. They make decisions like, I have diabetes, I'm not going to eat such and such. Or, so that's something that's, like, really kind of gives you a picture of why the results may be less convincing from just reading the conclusions. Sorry.
So this is not statistics, but at the bottom of the first page it says the study was funded by the International Tree Nut Council.
Mm-hmm.
Does that need to be factored into our
Well, I
understanding?
would say that that's one of those things that's really hard to factor in. But, yes, of course.
Should that
I
be
mean,
Well,
they always should be disclosing it, and I think that they're always asked to disclose those interests. You'll see usually, the authors have no, interest in this, or they say they will. But if I were the New England Journal of Medicine, which is a super, I would put increased scrutiny on that because of that affiliation. I would perhaps ask them to say, like, how did you actually analyze your data? Like, I might want to put a statistician who's reviewing that their methods are correct, because the data are available. Like, these are not data that are proprietary. Like, the sort of doubt that you might have about how they did things, it's a lot less than you would have about, say, even a controlled experiment conducted by a pharmaceutical company has a lot to gain, and they're going to hide the data for privacy reasons usually. But so I would say, sure, that does. As a journalist, what more can you say than say they were funded by it? We don't know what role that would play. There's nothing probabilistic that we can say about that.
Well, it doesn't say that they didn't have any influence, just...
Oh, right. It doesn't say that. Right. I mean, I'm sure that's what they're claiming, that they didn't have influence because they made a study. So it does say, I mean, they are stating and publishing this, that is what they found in the data. Whether they were, I mean, I think it's an implied bias, absolutely. I will say that over the years, I have found a lot of people who don't have vested interest in specific things who nonetheless really do have vested interests because people believe in things. Right. So actually the autism one is one of these big ones where most of the people who are writing poorly done studies have a huge vested interest in, like, maybe they have an autistic kid, they maybe have something going on, they really, really believe that vaccination causes autism. So they do these studies and you sort of know what they think before they start. And that's actually really unfortunate. But they may not have any vested financial interests. Sometimes they do, actually, that's come up too, but sometimes they don't. So you have to be careful to not only assume that the only financial interest has to do with that, because it's also like, anybody in a university setting has a lot to gain from publications. Mm-hmm. So just the interest of having a publication can bias people. So in this case, they may in fact have gotten personal money from that organization, or they might just have had money that supported their research. But it goes the other way too, that the research is interesting to that company, or to that organization, so they'll fund them rather than necessarily like in order to create that research. So it can go, it can go both ways, I think is. Yeah.
Some data out there in terms of like doctors getting money from drug companies, but is there one for like just researchers too that get funded, by the Tree Nut group or anything like that? Is there anything like that?
I don't know of anything that points to that directly. There are, this one here, it's not clear at all to me that they paid those people to do the study. They might have, But the other thing they might have done is like paid their summer salary what they might have otherwise paid on an NIH grant or something. So it's not always even clear like what that mechanism is here. But I don't know of any like central, unfortunately.
So on that note, I
Sorry.
apologize that we have to wrap it up. You've all figured out by now that the mug is like the hook, right? When I come out with the mug, we're done. But I do want to present you with an Evelyn Y. Davis Studios mug
thank you.
to take with you. This is our new studio that just opened a few months ago, and so you can take it back to George Mason and talk to your colleagues about what webinars you'd like to do with them.
Oh, excellent.
Thank you. This was
Great.
great.
Thank you for inviting me.